good afternoon, everyone. It's a great pleasure, and welcome to this session. I think it's number 6 of the Week of Science. So it's a great pleasure to see as many of you here, of course, and I'd like to start by thanking Fouad Laroui, Saad Tazi, and also Reda Ben Kiran for having organized yet another week of science in a series that is steadily becoming an important feature of UM6B's culture and scientific culture. So we have here a platform that encourages scientists, PhD students, researchers, and scholars to exchange and inquire about what hovers over the other side of their respective fields of and expertise. So this session is entitled Harmonizing Complexity, Perceptions by Natural and Social Sciences. As you can imagine, we are trying to conquer spaces that have become hidden to us, dare I say. Natural and human scientists occupy conventionally not only separate spaces, but separate times too. The fact is that the scientific method and science in general has steadily become specialized, too specialized, particularly in the last 2 centuries, which coincides with, surprise, surprise, the emergence of modernity. And the paradigm that preaches specialization became the norm, and those seeking to understand the self and life itself. So indeed, many wondered why I have chosen to mix, welcome Ali, to mix in today's session 2 areas that are seemingly different one from the other in a discussion that is already complex as it is, and I have resisted to answer because, honestly, my arguments were of the intuitive kind, so they would not make a lot of sense. I'm rather engaging together with my guests and with all of you today in a rehearsal that will help us speak to each other, discover the common denominators, social and human scientists, and maybe even inspire and be inspired to shed some light on concepts that might or might not be familiar to each one of us. So together we will inaugurate a UM6B discussion between natural scientists and that of philosophy and culture. And I believe we couldn't have chosen a better subject than complexity for the purpose. So before we get in the subject, let me start with some ground notions. I have a presentation here. Sorry for this. Okay. There we go. I'm just going to sit down, I think. So, first, it is worth noting that complexity has proven to be a fundamental feature of our universe that is not amendable to our traditional methods of modern science. Nevertheless, a proper formulation to structure and give definition to the broad framework of complexity, including complexity theory, is yet to be developed and is therefore presented as a composite of 4 major systems that encompass the main perspective on complex systems. So I think very, very briefly and simply have the 4, the self-organization, the complex adaptive systems, that comes largely from cybernetics and computer science, the network theory driven by driven data science, and of course nonlinear systems, which comes largely from physics, mathematics, and the study of far from equilibrium process chemistry. But we will not get into complex theory and its intricate details, as I believe they are treated by experts in the other sessions. Instead, I want to focus on exploring the notion of complexity, a friend or a foe, which is the title of this whole week, but from the different perspective of the scientists giving lectures today, and also from our panel. To set the tone, I will share some of my experience, and it is related to the complexity emanating from the nonlinearity of plasma physics. What I found out is that trying to model a complex system using traditional linear systems theory is like trying to put a screw through a wooden board using a screwdriver instead of a hammer. Or rather the opposite, using a hammer instead of a screwdriver. So the fact is that I was simply using the wrong tool, of course, because that is the only one I had. But before I elaborate more, and for those who are not familiar with the field of plasma, let me state some facts. Plasma is known to be the fourth state of matter, and there you have the sun, it's plasma. And the other three, of course, being solid, liquid, and gas. And plasma is the most abundant element in the universe. More than 99% is plasma. Nevertheless, plasma is probably the least studied state of matter. And I'm sure there are many reasons for that. But the fact that plasma is a complex, nonlinear system definitely doesn't help. So, meaning that it is governed by, when I was talking about nonlinearity, it's governed by laws that are not necessarily Maxwellian or Newtonian as we are used to. So, but it was exactly that, I think, that intrigued me personally, and surely many of my colleagues to study it. Its inherent complexity. Complexity was, for me, an invitation to understanding. And at least that is how I saw it. Now, just a sign of warning for a researcher dealing with nonlinear systems, the fact that you're dealing with nonlinear systems might mean that you have to manufacture measurement devices yourself. So the work is much multifold, doubled as a result of the non-usual environment that you're working on or the subject that you're working with. So together with colleagues, we developed measurement devices to acquire information about plasma dynamics and its energetics, which took us much time originally, but before we could switch from performing a few measurements a day to a few millions of measurements a day, thanks to digitalization, of course. Now, this of course helped speed up our way to understanding, but there was a secret. In almost every measurement using sophisticated electronic equipment, a certain degree of approximation was usually used. The approximations used in measurements have as a goal to minimize complexity and to render that nonlinear environment that we're working on more linear. So that was the whole idea always, to bring down the complexity using filters, attenuators, using, solid state stuff to bring down the complexity. So in other words, what we measured is an approximation of reality, while performing an exact measurement is actually not only difficult and time and resources consuming, but also very, very complex. So to better illustrate this complexity, let us look at some details. To measure plasma dynamics, so you use typically a probe like this with a tip that is metallic, and you run a bias voltage through it using some resistors and a voltmeter, and you have a power supply and everything, and you run a current through that to get a curve like this as you're changing the voltage from negative to positive, attracting ions here and attracting electrons as you move up. The resulting curve holds much information about the plasma charge density and a lot more information about the temperature, the plasma species, the energy distribution, and so on. And of course, that information needs to be decodified, once again using digital filters and approximations. So to summarize, I have described very briefly a measurement that uses equipment that is manufactured from components based on linear understanding of materials, and that is used to measure plasma, which is a nonlinear environment. And the results are mad fluctuations, instabilities, forbidden areas of measurement, and so on. So what do? We try to tame the results and bring in even more filters, data, and this time digitally, to decrease that complexity and to make the curves much nicer to look at and to deal with. So what we want to always do is to bring back things to our intuitive way of looking at things. That's what we're trying to do, even as scientists sometimes. Even we don't notice that sometimes, but that's really what happens. But didn't I just say a minute ago that complexity is an invitation to understanding? So now I'm saying the opposite of that. And I think, so this is what I mean with the fluctuations and all that, but I think more interesting is this thing. So basically there's an increased complexity as an invitation to understanding, reaching a position, at which point there's a trigger to actually decrease complexity, because that's the invitation for understanding now. And this keeps happening towards some goal, and what it is, I don't know. But I guess it's the process itself that is most important. Probably there are no goals at the end of that. So I seem to be riding a sinusoidal wave here, where the change from increasing to decreasing complexity seems to be triggered by an event, don't you think? But I know I'm not alone. Literally every researcher I have spoken to about this subject, independently of the field, seem to agree with the fact. What I have shared here is a telling example of how complexity plays a unique role in contemporary science. This emerging post-Newtonian paradigm, well exposed in general relativity and quantum dynamics, presents a core challenge for the 21st century. And this new paradigm seems to deeply question the way we see the world and our environment. So this leads me to a few questions. And I hope that the panel today will treat some of them. The first one is, what is understanding? I think I already mentioned a few words about that. And could it be an objective in itself, understanding, or is it the path? Or just a means to an endless process? And the second question is, what triggers the need for increased decrease of complexity? Is it crisis, as Edgar Morin seems to have insinuated in his lecture, in this plenary lecture? Maybe. So throughout this week, we have listened to different angles and dimensions of complexity. Today, we want to add 2 dimensions to help us better conceptualize complexity and its position in our life as understanding seekers. To do that, we have with us a materials chemistry researcher, a culture and communication researcher. They will give 2 lectures, 45 minutes each, maximum, on complexity as they see it. Then we will have a short break before coming back to a panel discussion that includes a philosopher over there and an augmented humanist online with us from Japan. We have about 3 hours, I think. Maybe we can stay a bit longer. And I don't know how to do this, but I guess the best will be dedicate a chapter to engage our audience at the end directly with the questions and comments. I think this is probably what we'll be doing at the end, because I'm sure you'll have a lot of questions. We'll do this in two parts. The first will consist of two plenary lectures, as I mentioned. The second will be the panel after the break. So let's get started. I want to invite my first guest, Professor Jochen Schneider. His lecture will be entitled Materials Design and Complexity. Jochen is a professor of materials chemistry at RWTH Aachen University in Germany. His research interests are on the material science of thin films grown by plasma-assisted vapor deposition, with a focus on quantum mechanically guided design of thin films regarding thermal and chemical stability, as well as elasticity. Jochen has been awarded the Sofia Kovlevskaya Prize by the Alexander von Humboldt Foundation for Excellence in Thin Film Materials Research in 2001, and was named Fellow of American Vacuum Society, AVS, in 2013. In 2015, he was appointed as Max Planck Fellow and RWTH Fellow simultaneously. In 2020, he was the Bill Sproul Award and Honorary ICMCTF Lecture recipient. And in 2022, he received the Rudolf Jackel Award of the German Vacuum Society to recognize outstanding achievements in vacuum-based sciences. So with that introduction, I would like to invite Jochen to join the podium. And your